Hello, my name is Larry, and here we are going to talking about the denseness of the natural numbers. We are going to talk about the background of denseness of rational number. What we need to learn about the property of denseness. The first one is we can know about how set of number is distributed in real number system. We will discuss later. And the other one is it is useful in proving approximation theorem and limit processes. Like I will give you the non-example is Lagrangian approximation. This one is derived from the lesson of rational number, but we are not covered today. This is the definition of denseness. Let S be subset of real number. For all real numbers A, B, and A is smaller than B, there exists a number C in S such that A is smaller than C and smaller than B, which is to say that C is between A and B. What it means? I will say that I will give you an example like rational number. 1 and 2 is rational number inside here. So of course, right? Like golden ratio and 3 over 2 is inside the 1 and 2, right? So this is the useful analysis. You choose randomly two numbers such that there has one specific number inside the set S such that A and B has including the number that has for the set S. So this is the level one, the fundamental property of a positive integer. We need to know the set of positive integers is not orderable. So in general, how can you prove that? Like give an example, 1, 2, 3, 4, and this one. Tada! This is the not bounded proof. This we are to prove positive integers is not bounded proof. But we cannot use this up because we want to rigorous proof. How can I prove? Using the contradiction proof. Assume that positive integer set is bounded proof such that for any positive integer such that there exists the real number such that is x is smaller or equal to c. And then using the cell and flow function, notice that c is between cell c and flow c and cell c. And then this cell c is smaller than cell c plus 1. So which is, and then we can know that cell c plus 1 is also integer, positive integer. So cell c plus 1 is larger than c. It contradicts that any positive integer x is smaller or equal to c. So we prove this by contradiction proof. How about another one? Archimedean property. Archimedean property says that for any positive number s, there exists a positive integer n such that n is larger than s. It seems it's very abstract. We also use the contradiction proof to see to discover this proof. So write down the logical expression of A is this one. And then we write down using the contradiction, you get the statement is this one. And notice that n is the positive integer set inside n is inside the positive integer set. And then s is a upper bound. So s is not or equal to s. Level one is already told you set of positive integer set is not upper bound. It's not proof. So it contradicts the level 1 and already proved the level 2a. How about level 2b? Using the level 2a, convert the positive number s into 1 over s0, and then there exists the positive integer k such that k larger than 1 over s0. This is for derived from the level 2a. And then we our target is to achieve this proof. So how can we do? Move the epsilon into left side and k to the right side. So we can to prove this one. So we can use the Kindle property right now. And then another one is existence of integers in unit intervals. So this is the highlight word. Exactly one integer. What it means? We see the word first. For any real number c, there is exactly one integer in the interval, this one and this one. And then exactly one integer means the integer exists between this interval and also integer is only one inside this interval. This this idea we want to prove. So you must prove the integer exists in the interval and then also prove only one integer inside the interval. So you are not only prove the existence, you are going to prove uniqueness. We will use the definition of cell function and flow function to prove the statement. For the A is using the cell function, right? So here you notice that you choose randomly real number like this one, and then this one is between two and one, and then two is the cell function like root of two, and then your cell function of the root of two is equal to two, and then at the left side is the cell c minus one. So this is the function became okay. Cell c minus one is smaller than c and also smaller or equal to c, and then I plus one. Why I plus one? Because I want to achieve this goal. So C and C plus one, and then including and not including. And then you notice that cell C is integer. So we have to prove that cell C is inside C and C plus one. So we have proved that this is existent integer inside this interval. How about uniqueness? Assume there has another integer in C and C plus one. Then m must be larger or equal to cell C plus one, and also smaller or equal to cell C minus one. But here you notice that these two numbers are not included in this interval. So both are not in this interval, we are not in A. And then the 3b is similar to the 3a using the flow function, and then you can done it. Here we are going to prove about the denseness of the rational numbers. The set of rational numbers Q is dense in the set of real numbers. Here, how we can say that? How about this theorem say that? It means that you randomly choose any real number, like 1 and 2, and then there exists one rational number between 1 and 2. This is what he wants to talking about. So for any real number a, b in real number, there exists c in rational number such that a, b has inside the rational number here. So what we can prove? We assume that this is a real number m is such that a is smaller than b. This is very important because we want to use the accumulator property. Choose the positive number b minus a. Lemma 2b. Remember that this is the for the theorem for the lemma for this one here. And then we are going to use the positive number b minus a that exists the integer k such that b minus a larger than 1 over k. And then I move the positive integer to left side, kb minus ka larger than 1. And then I move the minus ka into the right side. So kb larger than 1 plus ka and larger than ka. And then you notice that this one, I can use the lemma 3 to prove that there exists there exists integer n inside here. So ka and ka plus 1 inside has positive, sorry, not positive integer, it's integer n. So I can imply that ka and kb between has an n. Since positive integer is k, we can write, and then we can divide that into this form. A and b between them has m over k, and m and k are integer, then m over k is rational. We are done. Next, we are going to talk about how rational number can use this to prove the next corollary and example. The next thing is density of irrational numbers. Lastly, we have already proved rational number is less in the rational set of real number. Here is rational numbers is less in the set of real numbers. Using theorem 1, consider the real numbers a over root of 2 and b over root of 2 because we are already proved the theorem, this one. So we can choose the ab real number. And then there exists the rational number q such that inside here, a and b inside the here has a rational number q. And then I multiply with root of 2. I realize that root of 2 multiplies with q is still rational because irrational number multiplies with rational number is still irrational number. Therefore, between n and b, there exists the irrational number between interval n and b. Another one is corollary 2, density of q in R. Lastly, in theorem, we have already proved that any two real numbers, a and b, inside has one rational number. But here, I want to prove that any two real numbers inside has infinitely many rational numbers. So we are going to use the contradiction proof. There exists two real numbers between which there has n rational numbers. So we have n rational numbers. But what I can say about this one, I can also use the denseness of rational number. Q1 and Q2 I can consider as this is the real number. Inside also has rational number here. So this is the from the derived one. So I choose any index j from this from 1 to n. Then qj and qj plus 1 inside here has also rational number inside here. So by derived one, there exists a rational number r such that qj and qj plus 1 inside has the rational number r. Where we can say, because we have already assumed that we have Q1 and Qn has n rational numbers, but there has extra one, which contradicts to the assumption. So any two real numbers has infinitely many rational numbers. And the last one, going to use the example here. Find the supreme density. So I given the definition, exponential function is strictly increasing, which is this definition, and then I assume that set S is this set. I want to prove that S has no maximum and no sub S is equal to E. Okay, how we can prove the A first? We prove the A. Obviously, we can use the contradiction proof. So are using the contradiction. Suppose S has maximum. What's the maximum mean? There exists the real number C such that C is inside set S. And also for all X in set S such that S is larger or equal to C because C is the biggest one. So I call the maximum number as e power c such that for all p e power x in set S, then e power s is smaller or equal to e power c, where we can express that s is larger is smaller or equal to c, so it is smaller or equal to s is smaller or equal to c. So this is the definition of strictly increasing, but here we are going to use the contrapositive way. And then notice that C is also smaller than 1. And also C is a rational number. So we can use the derived one that exists the rational number K such that K is between C and 1. And then we can imply that e power C is smaller than e power K. So it contradicts because e power K becomes to the biggest another one biggest one. So to prove the supremum S is equal to E, how we can prove that? This statement is equivalent to E is the least upper bound. So notice for all x in X, such that x is smaller than 1, and then this statement. Because the definition is stated that it is smaller than 1. And here, since by definition we can find that E is the upper bound of X. Also, since E is upper bound, so we can say that this upper bound sub S is smaller or equal to E. This is by definition. And then I want to prove that sub S is larger or equal to E. So here I want to use contradiction proof. Assume that this upper bound sub S is smaller than E. Then I can say that let the E power L is equal to sub S for some L is smaller than 1. And then I realize that there exists a rational number Q such that in between L and 1, and Q is also a rational number by using the denseness of rational number. Here, e power Q is S. So sub S and E as e power Q here. So it contradicts the definition of sub S because sub S is already maximum in the is already larger or equal to the element in set S. So sub S is larger or equal to E and sub S is smaller or equal to E, then we can imply that sub S is equal to E. That's for today. Thank you very much.